Hey there, and welcome. Today, we are diving into a really powerful tool from the world of physics and engineering. It's one of those things that lets you cut through a super complex problem like it's nothing. It's called the Buckingham Pi Theorem, and trust me, it's a brilliant way to find simplicity in things that seem, well, impossibly difficult.
Okay, so to get our heads around this, let's start with a classic puzzle. Just picture a simple sphere, maybe a baseball flying through the air, or even a raindrop. Now, how would you figure out the drag force that's acting on it, the resistance it feels? It seems like a pretty straightforward question, but once you start digging in, you realize it gets complicated really, really fast.
All right, so to even begin to understand this drag force, we've got to figure out all the different things that are influencing it. And as you're about to see, it's a whole lot more than just how fast the sphere is moving.
So of course, you've got the drag force itself. That's the thing we're trying to figure out. But it also depends on the sphere's size, right? Its diameter, and its velocity, naturally. But that's not all. It also depends on the fluid it's moving through. Things like the fluid's density and its viscosity, which is just a fancy word for how thick or, syrupy it is. Now just imagine trying to run experiments where you're changing all 5 of these things one by one. That would be an absolute nightmare, a huge time-consuming headache.
But what if I told you there's a way to just boil this whole thing down? A kind of elegant recipe for cutting down the number of things we have to worry about. Well, there is. And we have an American scientist named Edgar Buckingham to thank for it.
So here's the big idea behind the theorem. It says that if you have a problem with, let's say, n variables, and those variables can be described using j fundamental dimensions, basic stuff like mass, length, and time, then you can actually combine them all into a much smaller number of meaningful dimensionless groups. And the formula? It's beautifully simple. The number of new groups, which we'll call k, is just n minus j.
Now, I want to be clear, this is way more than just some clever math trick. This is a method for actually revealing the hidden physics of a system. It helps us pull back the curtain and see the fundamental relationships that are buried under all those separate variables.
So the big question is, how does this actually work in practice? Well, let's apply it to our drag force problem. It turns out there's a pretty straightforward 6-step recipe that'll take us from those 5 messy variables to a much, much cleaner answer. Okay, so this is basically our roadmap. We're going to walk through these 6 steps together, and you'll see exactly how this powerful simplification works.
All right, step 1. And hey, the good news is we've already done it. Remember those 5 key players we listed out earlier? Force, diameter, velocity, density, and viscosity? Done.
So that means our number of variables n is 5. Easy enough.
Okay, moving on to step 2. We need to identify the fundamental dimensions for each of those variables. Now, pretty much every physical thing you can measure can be broken down into a combination of just a few fundamental building blocks. For problems like this, in mechanics, those building blocks are mass, m, length, L, and time, t. And what's so cool is when you lay it all out like this. A force, for example, is really just a mass times an acceleration, which breaks down to mass, length, and time. Velocity? That's just length over time. Density is mass over volume, or a mass per length cubed. So when we actually write out the fundamental dimensions for all 5 of our variables, you see this amazing pattern. They're all just different combinations of m, L, and t.
So, because every single one of our variables is built from just mass, length, and time, our number of fundamental dimensions, j, is 3. All right, step 3. This is where we get to the core of the theorem. It's time to plug our numbers into that simple formula, k equals n minus j, and see just how much we can simplify this problem. And there we have it. K equals 5 minus 3, which is 2. We're going to have 2 pi groups. This is huge. It means that our entire complicated problem with 5 different things to track can now be completely described by the relationship between just 2 new, much more powerful groups. Okay, step 4. To actually construct these 2 new groups, we need to pick a few of our original variables to be like our foundation. The general rule here is to choose a set of what we call repeating variables, one that covers geometry, one that covers motion or kinematics, and one that covers mass properties. So, for our drag problem, the perfect choices are pretty clear. We'll use density for the mass property, diameter for the geometry, and velocity for the kinematics. These 3 will be the building blocks for our new pi groups.
Step 5 is the construction phase. It's actually pretty cool how this works. We take our 3 repeating variables, density, diameter, and velocity,
and we combine them one by one with the variables that are left over. In our case, the leftover ones are the drag force and the viscosity. And doing that is what gives us our two new groups, which we'll just call Pi 1 and Pi 2.
Now, full disclosure, there's a little bit of dimensional math that goes on behind the scenes here. You have to combine everything in just the right way to make sure that all the m's, l's, and t's completely cancel out, leaving you with a pure number. But we're going to skip over the nitty-gritty algebra and jump right to the really elegant result.
Because after all that work, we get to the real payoff. This is the aha moment, where the true magic of this theorem just clicks into place.
Just look at this transformation. On the left, we had that messy function where the drag force depended on 4 other things. But on the right, look how clean that is. It's an elegant relationship between just 2 new groups. That first group on the left side of the function, that's what engineers call the drag coefficient. And the group on the right, that's the one and only Reynolds number, a super important value in fluid dynamics that basically tells you if the fluid flow is going to be smooth and orderly or chaotic and turbulent. Think about it. We've gone from 5 separate variables down to a relationship between just 2 incredibly powerful and meaningful groups.
Okay, so you might be thinking, that's a neat trick. But the crucial thing to understand is that this isn't just some abstract academic exercise. This has massive real-world implications.
I mean, think about it. Because we now know the physics depends on these special dimensionless numbers, engineers can do amazing things. They can build a small-scale model of a new car or an airplane, stick it in a wind tunnel, and as long as they make sure the Reynolds number in their test matches the Reynolds number of the real thing, the results will scale up perfectly. This saves an absolutely unbelievable amount of time and money in engineering. It's used for everything from designing ship hulls to figuring out fluid flow in pipelines. It's basically the foundation of how modern experimental fluid dynamics is done.
And all of this leaves you with a really fascinating thought, doesn't it? The Buckingham Pi Theorem shows us that even the most tangled, complicated-looking problems can have a simple, elegant structure hiding just beneath the surface. It really makes you wonder, what other complex problems out there in science, in economics, maybe even in biology, are just waiting for someone to come along and find the right dimensionless groups to unlock their secrets? Something to think about. Thanks for joining me.